Students, today we are going to see memory management techniques in operating system. So, we all know what is memory. Memory is a small area where it's a temporary area and where we are going to store our data and instructions. And every program needs to be brought into memory before it starts its execution. And every program or all the process in the memory will be kept in a input queue, because from that input queue only the OS is going to select the process and give it to CPU for execution. And user programs, before execution, it goes through different steps. And every memory instructions or data needs to be binded in each phases, that is in compile time, in load time, and also in execution time. So, in compile time, if we already know the memory location, the absolute code can be generated. Absolute code is nothing but the memory address can be generated very easily. In load time, even if we don't know the memory address, a relocatable code will be generated by the operating system in order to point out the place where the data or instruction is stored. And in execution time, at the time of run time, the process can be moved from one memory segment to another with the help of the memory address for running the process. And the multi-step of processing of every program, every user program will be, we are going to give a source program. It could be a Java application program, or a C application program, or a C++ application program, whatever it is, we are going to give a program which is called as source program. And that source program will be compiled by the compiler and it will be converted to a object program or object module. So, at the compile time, the main work is to convert the source program into object program. And after that, any linking files were there, that linking files will be linked at the time of loading, and the module will be, after linking, it will be loaded, and it is loaded by the loader into the memory, and that is happening in the load time. And after the process is completely loaded into memory, if any linking of system programs needs to be done, that will be done. That is called as dynamic linking, because now it is an execution state. So, whenever the files are linked at the execution state, then it is called as dynamic linking. So, after doing all the dynamic linking, the process is going to, or the program is going to run in the with the CPU, and the output is given to the user. This is how each and every program or every application is controlled by the operating system. And before seeing into memory management, we should know what is logical address space and physical address space. The logical address space is given by the user, because the user will not know the actual address space where it is stored in the memory. Take for an example, I am giving a 10 line of program, and that I don't know that 10 line of program where it is stored in the memory. Suppose I want to access the third line, means I have to give the logical address as third line of my program, because the OS doesn't know where the third line is stored. It needs to do some processing in order to fetch the third line of the program, and it will start its execution. So, the actual memory where the third line is stored is called as the physical address space. The user will not know the physical address space. Might be the third line of program will be stored in the 14,000th location of the operating system, but we don't know that. The operating system needs to take the value, the 14,000, and it will load that particular line and start its execution. And this is happened with the help of the memory management unit. So, in memory management unit, it will have a relocation register. So, relocation register, the main work of relocation register is to convert the logical address space into physical address space. So, we will see that. So, this is the diagrammatic representation of the relocation register. See, in CPU, the logical address which I am giving is 346. That means, in the 346th line of the program I want to execute. But the actual work of the memory management unit is, it needs to fetch the actual address, actual physical address. So, the relocation register will do that. The actual physical address starts from 14,000, because some memory space will be taken by the resident operating system. So, the remaining spaces will be allocated for the user's application programs. So, the relocation registers has taken that physical address starts from 14,000 only. I want to fetch my 3, 4 to 6th line. So what should memory management unit will do is, it will add the 14, starting location is 14,000, it will add the 14,000 plus 3, 4 to 6. So the actual location where the 3, 4 to 6 line is stored is 14,000 and 3, 4 to 6. So that will be given by the memory management unit, and the particular line in that location will be fetched and executed or done for processing. And the next one is dynamic loading. So what is a dynamic loading? So suppose in my program I have called a function called math function called sin of x. Okay, sin function. So this math function needs to be loaded only at the time of execution. That is, I have 10 lines. In my 5th line, I am using the sin function. That means the 4 lines needs to be executed, and whenever the 5th line comes only, it is going to call the sin function. So the commands with the instructions which is loaded into memory at the time of whenever it is called, or at the time of calling only, then it is called as dynamic loading. So what is the advantage is that it has the better memory utilization. That means once if you call the sin function, the sin function may contain 10 or 15 lines. So we will take it as 10 lines. Already I have 10 lines, and in my 5th line it needs to load the instructions given in sin function. So totally my programming lines now will be 20 lines. So the memory space is finally utilized only whenever the routine is called, it is loaded. That's why it is called as dynamic loading. So whenever you are using a large amount of code, it will be very useful. For example, I have told you about only 10 lines. Instead, if you are using 2000 or 3000 lines of code, and the function which you are calling is having again 10,000 lines of code, it is not that every time the 10,000 lines of code will be in your program. Whenever you encounter, or the OS will encounter that particular line, then the 10,000 lines of code will be loaded. That is called as dynamic loading. And there is no need of any special support for the operating system. It will automatically do the dynamic loading process. And the next main topic is dynamic linking. So dynamic linking is nothing but at the time of execution, stub is maintained by the operating system. That is, the memory space will be pre-allocated for the functions, and that is called as stub. So every time any function is called in your program, the function code will be stored only in the stub, and if the process is over, the stub will be cleared and loaded with some other functions if you call. So the stub is replaces with the address of the routine which you are going to execute at the runtime. And dynamic linking is particularly available for library functions, like I have told you, sin, cos, mathematical functions, sin, cos, or any string functions. If you use replace, copy, string copy. So if you use whatever functions in libraries, then the stub will be loading the functions code in that area. Then the memory will execute the complete program. And the next concept we are going to see is overlays. So overlays are nothing but not every time all the content will be stored in the memory. So some content is needed for some time, and some other content is not needed for a long time. So those contents will be stored in a separate place, and whenever needed, the content which is inside the memory will be taken out, and the content which is needed now will be stored in that place. So this is called as overlays. So with this overlays technique, the memory space is properly utilized. Suppose the content A is having 100 lines and content B is having 100 lines, and you can store only 100 lines into the memory and it will be executed, and whenever it is not needed, that 100 lines with process A will be replaced with the process B. And implemented with no special support. This is also automatically done by the operating system. So this diagram will depicts that. So you have a symbol table for 20K memory space, common routines are of 30K, and you need an overlay driver which loads and reloads the processes. So that overlay driver has taken 10,000 memory space, 10K memory spaces, and you have remaining some memory spaces. So in that memory space, I have 2 pass of process. In one pass it is 70K, space, and in second pass it takes 80k space. Not all the time you need to have pass 1 and pass 2 in the memory. Instead, whenever pass 1 is needed, that will be loaded by the overlay driver, and whenever it has been completed, it will be taken back and loaded by the pass 2. So memory space will be properly utilized, and this is done with the help of the overlay driver, which is doing all the work of swapping in and swapping out. So as I have told you, whenever the process is not needed, needs to be taken out, and whenever needed, it needs to be taken inside. The technique is called as swapping. It is otherwise called as roll out or roll in. And where the content will be stored, if you want to take out from the memory, where the content will be stored? The content will be stored in the backing storage devices, and whenever needed only, the backing storage device will managed, and the content will be stored into the memory. And the major thing is the swap time is called as the transfer time. So the total transfer time is directly proportional to the amount of memory swapped. That means depending on the memory only, the swapping will happen. So this diagram will tell you how the swapping is happening. So you have a backing store, and in the main memory, some space is occupied by the operating system, and in the user space only the process is going to be executed. In backing store, you have two process P1 and process P2. Now if process P1 is needed, process P1 will be swapped in. Now the diagram shows that process P1 was already there in user space, and it is swapped out to the backing store because process P1 is not needed now, and process P2 is needed now. That is swapped inside the main memory from the backing store. So this diagram will clearly show that how the swapping is being taken place by the memory. And a contiguous allocation. So what is contiguous allocation is, the main memory is divided into two things, one for resident operating system, another one for user process, as we already know. So the partition, this is called as partitioning memory. So the partition could be a single partition or it could be a multiple partition. So what is a single partition is, the relocation register is protecting the operating system. Any of the application program should not enter into the operating system and do any changes, and similarly any of the system programs should not enter into the application programs and do any changes. So the protection is maintained by the relocation register in the single partitioning. And how it has been accessed is given in this diagram. You have a CPU, and we are giving some logical address, and suppose I am giving I have 10 lines of instruction, and I want to access the third line of instruction. So my logical address will be, the user will give only third line. So that is checked with the limit register. So you need two registers for partitioning. One is limit register, another one is base register. Base register is going to have the starting address of the process, and limit register is going to have the total number of lines or total number of memory space occupied for that particular process. See, suppose limit register is having 10, because I have only my process is having only 10 lines, but I want to access the third line now. So the logical address is 3, and what is the limit register value? It is 10, because I am having only 10 lines. It will check whether logical address is less than the limit register. Say for example 3 is less than 10. Yes, the user is actually accessing the correct part of the process. Suppose if the user is giving 15th line I want, actually the process is having only 10 lines, so the logical address is 15, limit register is having 10, so 15 is not less than 10. That means it will show that it's an addressing error. It means that a user is trying to access the part which is not available with the process, and if suppose it is satisfied, then it will add the relocation register value. What is relocation register value? My program is residing in a particular location, what I have told you, say, take it as an example 14,000. So 14,000 will be in the relocation register, but I want the third line, so 14,003. You add the relocation register value with the logical address. So 14,003 location, I am having my third line of instruction, and that will be fetched from the memory. This is how the hardware works for accessing a particular line of some or particular instructions and data which is residing in memory. And whenever you use the contiguous allocation technique, you can also have a multiple partition also. That means more than one process is going to be reside in the user space. That means you need to partition for all the process. So see here, you take this as an example. The operating system is maintaining some information about the partitions, where in which partition the process has been allocated, and also whichever the partitions are free for allocating some other process. So whenever a process arrives, it is allocated to the memory where it finds the free space. Here free space is called as a hole, HOLE, hole. And the process will be allocated to the large enough hole by the operating system always, right. So see here in this diagram, you have operating system and you have three processes, 5, 8 and 2, and whenever the process 8 has been executed, it will be taken from the memory, and that space is very empty now in the second diagram, which means that it is the hole. And after that a process is arriving, that is process 9. So it will take the space or the hole which is free enough, and will and the OS will store that particular process in that space. So the process 9 is stored in that hole, and after that process 10 is coming. Again you have the same space, again it will be stored next to the process 9, and totally you still have some hole for holding some more process. And you have a problem with this. This is called as dynamic storage allocation problem. So what is the allocation problem? The OS is storing in the place wherever it is free, but you have a problem with that. How will you eradicate? So how to satisfy a request? Suppose I am having a 10 process, and all the 10 process needs to be stored in a particular hole. For example, I am having only 1000 K of hole, but the process length is 2000. So how can I manage and place it in that whole part? So I have to think. So for that I can use any of the fit. One is first fit, best fit, or worst fit type of allocation. So what is the first fit? Allocate the first hole that is big enough. Say for example, I want to allocate a process which is having 10,000 space, but I am having the hole which is of space 20,000 and 130,000 hole is there. 120,000 hole is there and 30,000 hole is there, and I am having a process of 10,000 memory space. So where will I allocate this 10,000 memory space? If I am using a first fit, I want to allocate it to the big enough space. That means I am having 30,000 as a big enough space where I will allocate the 10,000 memory space of process. The remaining 20,000 space will be free now. And what is best fit? Best fit is allocate the smallest hole that is big enough. So suppose I am having a 20,000 hole and also 15,000 hole. So where will I allocate it? If I am using best fit, I have to allocate in the 10,000 hole, because that is the smallest enough hole which is available. Right. And what is worst fit? Worst fit is allocate the largest hole. That means you need to search completely with the holes which is available, and you have to choose one the largest hole. So I am having a 10,000 line of process with me, and I have 20,000 hole, 30,000 hole, and a 50,000 hole. So where will I allocate it? I will allocate it only with the 50,000 hole, because according to worst fit I am choosing the maximum space which is needed by the process. So which one is best? If you analyze, first fit and best fit is best. All other, that is worst fit, is not okay all the times, because I am having 10 process now, each one is having 10,000. I cannot search for the biggest hole in the list of process or list of memory spaces. That will take time, and for all the process I cannot get the big enough hole. So that's why worst fit is not okay. It is better to use first fit and best fit methodology. And when you are allocating this process into first fit or best fit methodology, you will get a problem called fragmentation. What is fragmentation? As I have told you, you have two types of fragmentation: external fragmentation and internal fragmentation. As I have told you, I have 10,000 lines of program, and in the memory you have 20,000 memory space and 30,000 memory space. There I am placing this 10,000 in 20,000, means 10,000 is remaining. If I am placing it in 30,000, 20,000 is remaining. So see here, what is external fragmentation? Total memory space exists to satisfy a request, but it is not contiguous. What is not contiguous? If it is not continuous space. So if I am having a memory space like this, 5,000 and 5,000 in a different holes. So according to external fragmentation, what I will do is, this 10,000 line of code will be allocated in one place where I have 5,000 hole, and where I have another 5,000 hole, I will allocate the remaining 5,000 lines of code. So what happens? It is not a contiguous one. Then it is called as a external fragmentation. And what is the internal fragmentation is, I have allocated the maximum size for the process, but still I find some spaces remaining in the whole, then it is called as internal fragmentation. So take for an example, I have 10,000 lines of code now, and I have 20,000 or 25,000 lines of memory space, 25,000 memory space is available. I am placing this 10,000 lines of code. So we will make it as a smaller one. Suppose I have 12,000 memory space, and I want 10,000 of my lines of code needs to be placed, and I am choosing this whole, and in the 10,000 is allocated, but still you find some space available, that is only 2,000. So this 2,000, if it is cannot be allocated for another process, this 2,000 whole will be remaining for a entire period of execution time. It will be still whole only, it cannot be allocated because it's a smaller amount comparatively to other wholes. So definitely no process will be allocated at that particular whole, then it is called as internal fragmentation. After allocation, if you find any memory space still available, then it is called as internal fragmentation. External fragmentation is you yourself dividing the process into two different modules and placing it in the holes, then it is called as different holes, then it is called as external fragmentation. So the external fragmentation can be reduced with the help of the compaction. What is meant by compaction is, you have to merge the memory space into a smaller part. You have 30 students in your class, and you find some places in the classroom is empty. So what you will do, you will ask the last bench students to come front, so that the last space will be very clear. For that, if any new student or some student comes for the class again, you will ask them to place over in the last bench. So that is called as compaction. So making all the process coming together so that a large whole will be given for other process to get allocated. So that is called as compaction technique. Right. And the operating system, it uses some techniques to access the process in the memory. So that one is paging technique, another one is segmentation technique, and it also uses both the things, segmentation with paging. So what is paging technique is, the logical memory is divided into logical memory is divided into pages, and the physical memory is divided into frames. That means my program will be divided into pages, and each and every page of my program will be stored in a corresponding physical memory, in the corresponding frame in the physical memory. So every page needs to be mapped with the frame in the physical memory. So this work is done by the operating system. The operating system maintains a table where it will have the page number and the corresponding frame number. So whenever a process needs to be allocated, then it will check the free frames, and whenever process needs to be executed, the table will be checked, and it will process that particular it will do the execution for the process in that particular memories, from that particular memory space. So you need to transfer the physical logical address space into physical address space. So that translation is done with the help of two variables. One is page number, another one is page offset. So what is page number is, the logical address space divided into pages, I have told you. So every page will be given a page number, and that page number needs to be compared with the frame number, and page offset is needed. What is page offset is? Base address of the instruction or data. Say take for example, I have a program with 10 lines. So what is the base address? It is stored in the 14,000th location, means that is the base address. So page offset is totally how many spaces allocated for that particular pages or particular file which you have divided into pages. So that is called as page offset. So with these two things, you are going to access that page in the frames which is stored. So in the you can see the address translation architecture diagram here. So CPU is there, and you are giving the logical address. Say for example, I want to access a particular page P. I have 5 pages in my process, and I want the second page to be accessed. So page number is now 2, And what is displacement? Displacement is inside the pages you may have any number of instructions. Take for example 100 instruction over there in second page means I want to access the 10th instruction of my second page. So the displacement is 10. So see here, so D is 10, P is now 2, P2 and D is 10. So see here, the page will be checked in the page table. As I have told you, the page table is going to have the page number and also the address of the first instruction starting, that is page offset over there in page table. So the OS will check the page table first, and in the page table whenever it finds that particular page P, it will find the frame number of that P. That's why it is given as F in the table. So the frame number has identified now, and that frame number will be added with the displacement. Why it is being added with the displacement? So take for an example that page number is in 14th location means the page that is F is 14,000 now. So 14,000 plus what is my requirement? I want to take the 10th page. That means where my 10th page will be residing, 14,000 and 10th location, my 10th line will be residing in that page. So therefore the page number is taken. Suppose I am giving the page number as second page, and in that second page I want to access the 10th line, that is the displacement, and the page table is accessed, the frame number is identified, and in that particular frame number I want to access the 10th line. So the frame number is 14,000, take for an example. So 14,010 is the displacement page where I want to whichever line I want to access in that page. So that is particularly accessed from the physical memory. This is how a page will be compared with the frame for accessing a particular lines. And you have some more diagrammatic representation of paging. In logical memory, it has been divided into 4 pages, 0, 1, 2, 3. So you will have a page table, and in that page table you will have the corresponding frame number. So what is that? A 0th page will be residing in first frame. You check the physical memory over there and check all the frame numbers 0, 1, 2, 3, 4, 5, 6, 7. So according to page table, page 0 will be in the first frame. You check the first frame, it is having page 0. And what is the second page? Number 1, and where it is residing in the frame number 4. You check the frame number 4, you could find page 1. And similarly, where is the second page? It is residing in the frame number 3. You check the frame 3, you could find page 2. Okay. Similarly, all the pages will be accessed. Okay. And whenever the process is being stored inside the frame, then it will update the page table. Then only we can use the page table for accessing that particular pages. So whenever a process comes, it will be divided into pages and a page table will be created. For every corresponding page, it will find the empty space in the physical memory, and it will allocate the page in the physical memory and store the frame number in the page table. Okay, right. And see here, I have told you every page may be containing some set of instructions that has been given here. In logical memory, again the 4 pages, but it is having, every page is having 4 lines of instructions. In the first page you are having 0, 1, 2, 3, that is 0th page. In the first page you have 4, 5, 6, 7. In second page you have 8, 9, 10, 11. And in third page you have 12, 13, 14, 15. So totally you have 0 to 3, 4 pages. And you see the page table. Again it's 0, 1, 2, 3. And where is that actually stored? You check there in the physical memory, it starts from 0 and ends with 28, right? So that is the frame number. So you check the 0th page A, B, C, D, where it is residing. It is residing in the frame number. It is starting with the frame number 20. Okay. So which frame it is actually? 0, 1, 2, 3, 4, 5. So every frame is now divided into 5 spaces. Sorry, 4 spaces for the line to be allocated in the memory space. So 4 line is there. So where the 0th page A, B, C, D values are, it is in the 5th frame. So it has been given in the page table as frame number 5. And similarly, you take the page 1. So page 1 is 4, 5, 6, 7, and it is having value E, F, G, H. You check where it is in the frame, physical memory. It is stored in the frame of 0, 1, 2, 3, 4, 5, 6. That means it starts from 24. So it is in the 6th frame. So you will have an address of 6 in the page table for page 1. And similarly, it goes. Right. And how the free frames are managed by the operating system? Because while allocating, it needs to check wherever the free frames available, the process will be loaded. So the OS needs to maintain the list of free frames available for allocating the process. So how it is managed, we will see here with this example. So before allocation, see here a new process is there which is having 4 pages 0, 1, 2, 3, and the OS is having a free frame list 14, 18, 20, 50. These are the frames which are very free for allocating the process, and before allocation the physical memory doesn't have anything, and after allocation you see here page 0 it needs to check the first free frame or the free frame which is available first in the physical memory. So what is the free frame available first in the physical memory? It is 13. So the page 0 will be first free frame is 14 in the free frame list. The page 0 will be allocated in the frame 14. Okay, and that will be updated in the process page table. So 0th frame is in 14th, 0th page is in 14th frame is updated in the page table. And you take the second page, page 1. So page 1, the next free frame is 13 now. So the 13 will be having a page 1, and the page table will be updated with the value 13 as the frame number for page 1. Similarly, it allocates all other pages which has been arrived with the help of the free frame list. Once the page has been allocated, the free frame list needs to be updated. That means 14 is already allocated now, 13 is allocated, 18 is allocated, and 20 is allocated. So what will be the remaining free frame list after allocation? It is having only 15th frame. Okay, so this is also automatically updated by the operating system. So page table will have two things. One is page table base register, another one is page table length register. Okay, I have told you the page table will be maintained by the operating system. Where it will maintain the page table? Again, it needs a memory space to be stored for the page table. Okay, so that page table where it is stored, that base address will be in the page table base register. And what is page table length register? How many pages are there for the particular page table? So the length will be in the page table length register. It indicates the size of the page. Okay, right. So every data and instruction needs memory access. Every whatever data the OS is using, it needs the memory access. It needs some memory space to store, and it is needed to access it whenever the user wants that data or instruction. And for giving a fast lookup for the data and instruction, it is using a cache memory or cache space which is called as associative memory or transaction look aside buffer, TLBs. Transaction look aside buffer, TLBs, and it is otherwise called as associative memory. So what is fast lookup? See, already a page has been accessed by the operating system, means that page details will be in the associative memory, where the page is residing, what is the frame number of the page will be in the associative memory. Not every time it needs to use the same address translation architecture to fetch that particular process, because it is having associative memory or a TLB where it resides the page number and frame number of a page which is frequently accessed. So we will see the diagrammatic representation, page number and the corresponding frame number in the associative memory. So whenever a process is needed, it first looks the associative memory, then only if it doesn't contain that particular page, then only it will go for the address translation architecture. Right. And how the paging hardware is done with the TLB. Suppose I find a particular page in transaction look aside buffer, then how it works? See this diagram, CPU is giving a logical address space, the page number is given. So the page number needs to be first checked in the TLB. In TLB, if it finds that page number and the corresponding frame number, then it is called as TLB hit. That means it has found that particular page in the TLB itself. It doesn't need to do that process again. So TLB hit, it is called as TLB hit. Once it finds the frame number, the displacement is added and the corresponding physical address is fetched from the physical memory. Suppose if that particular page number is not available in the TLB, means it is called as TLB miss. Then only it will go for the page table for choosing that particular frame number. And it will choose the particular frame number. That is the address of the physical memory. Frame number is nothing but the address of the physical memory. As it finds the address of the physical memory in the page table, then it will add the displacement and the corresponding physical memory is accessed for the particular line of a program. Okay. So this is how paging hardware with TLB is done. Two things you have to remember. One is TLB hit, another one is TLB miss. If it founds a page in the TLB, then it is called as TLB hit, and if it not founds a page in the TLB, then it is called as TLB miss. Right. And how the memory is protected. So you need protection for everything, because the computer is accessed by not only by single person, it is accessed by more number of people. So each and every part of the computer needs to have some protection. So similarly, we have to protect the memory. That means no other process should not access the memory for unwanted information. It should not take any information which is not needed by the process. So you need to protect the memory. How we can protect the memory? With the help of one bit needs to be added with the page table, that is called as valid bit or invalid bit. If a particular page is available in the page table, then the valid bit will be updated with 1. If it is not available in the page table, it is filled with 0. So every time the operating system need not to check the page table for accessing a particular page which is not available. So once if it accesses the page table for a particular page, and if it is not available in the memory, it will check the valid bit or invalid bit. With that only it will move to the memory, physical memory. Otherwise the OS will not move into the physical memory for accessing that process, because it won't be there accessing that page, because definitely it is not going to be there in the physical memory. We have found that in the page table itself. Only if the valid bit is 1, it will try to access the physical memory. So this is a diagrammatic representation of the valid or invalid bit in a page table. So you can see 6 pages are there, and the corresponding page table is there, and you can see some V and I's. What is V? V is the valid bit and I is the invalid bit. Valid bit means the pages 0, 1, 2, 3, 4, 5 is available, but 6 and 7 is not available. So you can see that page 0, 1 to 5 is there, but there is no 6th page and 7th page. So if any 6th and 7th page is required by the user, it will check the page table and it will say, okay, it is invalid. That means it is not available in memory, and give a wrong page access, or the page is not available in memory to user. So the message will be displayed for the user. And the page table needs to be structured. So how will you structure a page table? Because every process will be divided into pages now. So every process will going to have a page table. So you will have the page number of pages is directly proportional to page tables. So that's why you have to make a structure for the page table. So that could be a hierarchical structure or a hashed structure or a inverted page tables. So we will see what is a hierarchical page table is. The logical address space of the page table will be divided into multiple page tables. The simple level is 2 level. You can also have 3 level, 4 level, multiple levels of page tables. So we will see that one by one. 2 level, in 2 level paging, you have addresses, that is P1, PI or P2, and D is the displacement, that is page offset. So you can see a 10-bit page number and a 10-bit, everything is 10-bit now. So a 10-bit page number and a 10-bit page offset for that. What is PI and P2? If the P2 is residing in a place and the address of the P2 is stored in another page table, this is 2-level page table. The address of P2 is available in another page table, that is PI, means the PI will be the first page table which needs to be referred by the operating system. Then only it can able to find that the second page table, that is P2. It could find the address of the P2 and it will access that P2 and it will find the particular process or particular instruction or data needed by the user. So this is a 2-level page table. So we will take as an example, in School of Computing Sciences, you have Department of Computer Science, Department of BCA and Department of MCA. So School of Computing Sciences is the first level of page table, and the 3 values, Department of BSc, BCA and MCA is the second level of page table. So you have so many schools available in our university. So many schools are there. In that I will find the first School of Computing Sciences, that is from the first page table, and then I will access the 3 values, the second set of page table, BSc, BCA or MCA, where I want my student, whether he is studying in BSc, BCA or MCA, I will find that. So there is a second level of page table, right? And 2-level page table scheme has been given here. You have an outer page table where you will find 1 to 500 inner page tables are available. So from that, whichever line you want, you can access it from the physical memory. In the outer page table itself, you have another set of page table which will have the values from 100 to 708 that can be accessed in the physical memory. And you have any number of 2-level page tables. In the second level, you can have any number of page tables, but the outer page table will be only one level. That is, one page table will be there, and the inner page table can be any number of page tables, right? And how the address is translated for the page table, you have a logical address P1 and P2. First it will find the P1, that is the main page table, that is all the schools available in our vistas, and that is outer page table. From that it will take School of Computing Sciences, and it will go for the School of Computing Sciences page table, that is P2, and in that page table it will select either BSc, BCA or MCA, where you will find the displacement. If the student is studying in BSc, you can find it in the physical memory. If he is in BCA or MCA, you can find it with the displacement in the physical memory. This is how the address is translated for page tables. And what is the hashed page table? So hashed function is any calculation is done. It could be a prime number calculation, or it could be any type of calculation. You can even divide it by 2, you can even multiply it by 2. So anything randomly you can do some calculation, and whatever value you get, that value will be taken as the memory space for that particular instruction or data. That is hashed page table technology. And whenever it accessing that particular line or instruction or data, again it will apply the same function, and it will find it, and it will find the address. And you can ask me a question, ma'am, I will be getting a same value whenever I do same type of calculation for some numbers. So it will be in a linked list format. So whichever values or instruction or data stored in the linked list, it will have the address of the next values, and automatically it is accessed with the help of the address stored in the next thing. So we will see the diagrammatic representation. For a logical address P, a hash function is applied, and the hash table is having a linked list. It is going to have values of Q, P and everything, and it is accessing a particular value R, and the displacement is added, because in R you may be accessing only one line or one data, so that is called as displacement, as I have told you. It will be added, and the physical address of the particular data is found, and the physical memory is accessed with that. Then the next type of page table is inverted page table. So there will be actually one entry in the physical memory, that is called as inverted page table, and it decreases memory storage. So the main advantage is, if you are having a hashed page table, any number of page tables could be there. If you are using any hierarchical page table, you will be having 2-level, 3-level, multiple level. So multiple page tables needs to be stored in the memory, so memory space is wasted. But if you use the inverted page table, the memory space is very less, it will occupy very less memory space for that. So we will see this in the inverted page table architecture. In CPU, I am giving a logical address, that is the inverted ID, inverted value address for that logical address will be given, and with that address it is going to find the page number, and displacement is added. So we will see a PID is search. So for every page you will be given a ID. Okay. So like if you want to search, if the person is in the BSc Computer Science, I want to search a particular student in first year. So how will I search? I will check the number for each and every student, that is a unique number. Similarly, the inverted page table is going to have a unique ID for page ID for every page, and the page ID will be given every time, not a page number. So the page ID will be searched in the page table. So that page ID will be, if it found, it will be added with the displacement. The page number is taken and the frame is added with the displacement, and you will find the address in the physical memory. So it is enough, the OS is going to have a ID for each and every page. So it doesn't need to have any levels of page tables. Instead, it is having only one page table which will have all the pages with the ID. So you are going to search the pages only with the help of the page ID. So it doesn't need larger memory space. And you can also have a shared pages. So what is the use of shared pages? Same page can be accessed by more number of processes. So that doesn't mean that every process needs to have a memory space for that particular particular page. So the page which is shared which is used by many processes can be stored in one place, and the address of that page will be stored in, or the address of that page will be same for all the processes. This is called as shared pages. Sometimes you people need to have a private code and data. That means each process will have a separate code and data. So if I want to have a sign function data, so the sign function data will be private for my process only. If another student has needed the data will not be provided to him. He will have a copy of that in the same memory. So what is the disadvantages? The same copy is available for all the users, but it is stored in different memory locations. The memory space is wasted. To avoid that, we are going to share the pages. That means we are going to store the content or the sign function which is needed for all the people or all the students. It is stored in a particular memory space, and that memory space address will be stored for stored in the all the page table accessed by the student and also the professors. So we will see that with this example. You have two process P1 and P3. So three process P1, P2, P3 and corresponding page tables. You could see the editor ED1 is common for three processes P1, P2, P3. So you have to check the page table of each process. You could find ED1 in the position 3, that is frame number is 3. You check the physical memory. In the physical memory, in the third frame, ED1 is stored. So you check the page table of all the process. It is going to have the same frame number 3. That means what? The editor is shared by all the process. Okay. So if it is a private code, the editor will be stored separately for process P1 in some memory location. That frame number will be updated in the page table for P1, and it is stored separately for P2 and P3, and that particular location, memory location, will be stored in the page table. Now it is shared. That's why the same memory location is accessed, stored in the page table and accessed by different users. Right. And the next technique is segmentation. So segmentation is every program in the previous paging technique, every part of the program is divided into pages, but here the every program will be taken as segments. If it could be a main program is a segment, a procedure whatever you have used as a separate segment, a function whatever you have used as a separate segment, method, object, local variable, stack, everything is taken as a separate segments. How it is going to access those segments? So this is the logical address space. It is stored as segments here: square root, subroutine, stack, symbol, table and main program. And logically it will have some frame number or physical address 1, 2, 3, 4 like that. That 1 will be stored in a physical memory space in some place, and 2 will be stored in a physical memory space in some space. So I need a table for this, and this table is called a segment table. Like page table, it is also going to have a segment base and segment limit. Segment base is where the segment actually starting address of the segment, where the segment is stored. So for example, if a segment is started from 14,000, so 14,000 will be the base address, and if the segment is having 100 lines of instruction, 14,100 is the end of that segment, and totally limit is going to have the number of instruction it is having 100. So the limit will be 100. Base will be 14,000 now, and the limit will be 100. And it is also going to maintain a table that is called as segment table. You will have a segment table base register and also segment table length register. What is segment table base register? Base register is going to have 14,000. Length register is going to have 100 here. Right. And in that segmentation table, you can also have a validation bit, that is 0. If the segment is having a particular line of code, if it is available in the segment, the validation bit will be 1. Otherwise, if it is an illegal one, that is, it is not available in the segment, means the validation bit will be 0 here. And the diagrammatic representation of segmentation hardware is CPU is here. You have a particular segment S, and in that segment I want to access suppose 10th line. So the displacement is 10 now. So it will check with the segment table limit and base register. Now I have a segment which starts from 14,000. So base is 14,000 for the segment. What is limit? 100 lines I have told you. So the limit is 100. So the segment table is first fetched. So it is having the limit and base, and the limit will be checked with the segment. Say for example, I have 100 lines now, and I want to access the 150th line of the segment. Is it possible? No, it is not possible. So if it is not less than, if it is greater than, what is the limit? 100, but I am giving a segment line 150. It is not available, so it is greater the limit. If it is greater the limit, the OS will show you the error. it is a trap. So it will show you the error, and if it is okay, that means I want to access the 10th line. So the 10 number is less than the 100 total limit. So if it is yes, then it is going to fetch the base address of the segment table, that is 14,000 for my segment, and it will add the displacement. What is the displacement? In the 14,000 segment, I want to access the 10th line. What is the displacement? 14,010 is the displacement. So where my 10th line is residing for the segment in the physical memory. So it is fetched. Right. So example of segmentation is given here. So many segments 0, 1, 2, 3, 4 is here, and corresponding limit and also base is here. You can check with the physical memory. So the page, the segment 0's base address is 1400. Check there in physical memory. In 1400, segment 0 is there. What is the limit? 1000 lines over there in segment 0. That's why it ends with 2400. And similarly for page 1, the base address is 6300. So in the 6300, segment 1 is stored, and what is the limit? How many lines are there? 400 lines. So 6300 plus 400, 6700, segment 1 gets finished. Like page table, it is also having a segment table for accessing the physical memory for the segment. And you can also have a sharing of segments. Some subroutines will be accessed by many number of processes. So that doesn't mean that all the process needs to have a separate memory space for that segment or subroutine or function. So see here in process P1 you have editor, and in process P2 also you have editor. So segment 1 is for process P1 is data 1, for process P2 is data 2. You check the page table for segment table for both the process. A segment table for process P1 is for page segment 0, the limit is 25286 and the base is 43,062. In the location of 43,062, editor is there, and it is having a length of 25,286 lines, and it ends with 68,348. That means you add the base with the limit, you will find the end address of that particular editor. So the same base address and limit value will be available in the segment table of process P2, because it is sharing the editor which is residing once in the physical memory. So the sharing of segmentation is also possible, right? And the next one is segmentation with paging. So if you combine the working of segmentation and also with paging, then it is segmentation with paging. It is otherwise called as multics. So it is used for very large number of problems. You can have a segment table and also page table for accessing. So every segment will be divided into pages, and the segment will be divided into pages, and the page table is there. So first we need to identify the segment whichever I want to access. In that segment, which page I want to access, I have to identify with the page table base, and if it is greater than means it's an error. The limit should be equivalent. If the limit is greater than, it is an error. If it is less than, the corresponding page table is identified with the frame number, and the frame number is added with the displacement. That is, in that page which line I want to access, it is added with the displacement, and the corresponding physical address in the physical memory is identified. So this is multics. That means you are combining segmentation with paging. So these are the techniques: paging, segmentation, and segmentation with paging are the techniques used by the operating system for managing the memory in order to give the user fast access of pages. Instead, if it stores all the content in a particular place, then we cannot be able to access any of the lines inside that pages or inside that complete program where it is residing in a big space of memory. It is not easily possible for the user to fetch the values, instruction or data for processing. So for that, it is using these techniques. So these techniques for managing the memory space for addresses, managing the memory space for instruction and data by dividing the addresses into pages or segments, or it uses both concepts. Thank you.